Well, good evening, everyone. Thank you very much for coming along tonight. It does promise to be a very exciting talk that we're going to have tonight. Something that isn't normal for the institute. Something different, and I'm sure you'll all appreciate that, especially seeing as what Rod has to tell us. So just a few little things. First of all, can you pay attention to the notices in cases of fire or whatever? Just follow the lights. Could you switch off your telephones, please? £50 fine if you are alerted. We can't have that happening, so take care. And after that, more or less, there is a situation where the bar could be open if anyone wants to have a drink after the talk. But we do need numbers, unfortunately. So has anybody show a hand if they would like to go to the bar after the talk? Oh, yes. Go on, I'll go there as well. Right. Yes. Oh, well, I'm sure they would too. David, could you mention that it's going to be okay? We've got about 10 or so. Lovely. Right, thank you very much indeed. Well, unfortunately, the President is available at the moment, so just a few little words saying what we are and who we are. And if you aren't a member already, please get a membership form and come and join us, because we have some absolutely splendid lectures on here. You will really enjoy it, and you'll get hooked, so you never, ever miss a month. You'll love it. We are very, very closely allied with the IOM3, and their lectures are equally as interesting if you can get along to any of theirs. But nonetheless, we're closely allied, so they supply all the what would you say, the credibility and such like, for examinations and such like. So we're very much a part of them, and they're very much a part of us. So apart from that, I was going to go through apologies for absence, but unfortunately the President isn't online, so I'll just make a note of what I know here now, and we'll be okay. We have the minutes of the last meeting, which was, let's see, it was, oh, heavens above, yes, it was one I couldn't get to and I missed, and I was really annoyed. It was Les Turnbull's North Eastern Railway Company promotion of the Stockton and Darlington Railway 50th anniversary. I'm sure that was quite controversial for any of you who came along here. I missed a really good one there. So could we have a vote on that? Some seconded? Oh, thank you, Norman. I'll just make a note of that. Proposed by Norman, if I can find a pen. Yeah. Right. Lovely. Right, well, we're not going to mess around here. In the early 1970s, the construction of a new reservoir was undertaken in the county of Rutland, initially titled Empingham Reservoir Project, and later being named as Rutland Water. Now, Rod Young here was very much a part of that, and just a little story about what he is. He's the Eastern Regional Manager for Barhale Ltd, and is past chair of the British Tunnelling Society, that's the BTS. He's previously given presentations to engineers on shaft sinking, smallbore tunnelling, handwork tunnelling, ventilation systems, and microtunnelling. So we've got a real expert here tonight, so we can expect something good. As chair of the BTS, his objective was to bring smallbore tunnelling to the forefront of the industry. And I think there's quite a lot more I could read from the script, but the fact is you're not here to listen to that, you want to hear what Rod has to say. So at that, I'm going to hand you over to Rod and let him tell you all about it. Thank you very much, Rod.
Thank you. Just put one thing right. I wasn't anything to do with this in the 70s. I know I look very young, but I'm definitely not that young. Right, as Steve says, I've been involved in tunnelling all my life, and apart from the bits that he just mentioned, I'm also involved in something called Tunnel Skills. I've also been elected to the North East Institute council as of December last year. And the other thing I'm involved with, which probably will affect everybody who's in the various bits of construction, are what's called the Civils Super Sector Competence Framework, which is coming out of the Grenfell fire issues. So that's something for everybody to look at for the future. Steve's kind of given an overview of what's on this first slide. I'm not going to go through it, but it's basically a bit of an outline of the Rutland or the Empingham Reservoir, and then get a bit more involved in the tunnelling aspects of the scheme. The reason I've kind of got involved in this is that a few years ago, just before COVID, we did an inspection into the tunnel, and it wasn't until I got involved in doing this inspection that I realised that Rutland Water wasn't actually fed by the rivers coming into the reservoir. It's actually fed by two pumping stations, what you would class as downstream of where the actual dam is. So that really was interesting. I've also attended a few local presentations by other peoples about the actual construction of the reservoir itself. The tunnels are constructed using what's called wedge block tunnels, and when I was a site engineer in the late 80s, we were constructing the same sort of thing for Lee Valley in North London. And since then I've also been involved in relining of some tunnels in London where the wedge block system has actually failed. So that's why I'm so involved and enjoy understanding what's come out of Rutland. And it's only about 10 miles from home as well. So we're going to cover a bit about the development to the approval process, a bit about the designing ground. There's two lots of shafts and tunnels. There's those that are connected to the back of the actual dam area, and then there's the main tunnels that take the water from the two downstream rivers up to the reservoir. Good bit about the segments because they're slightly unusual. Something about the shafts and the tunnels. The process all started after the reservoir at Pitsford was completed in 1956. The two engineers at the time who worked for Mid-Northamptonshire Water Board and Thomas Hawksley's consultant civil engineers, they moved over from that project and started looking at the location for the next reservoir. And the reason was that they were expecting that in the 1960s and onwards, there was big expansion plans for several of the local towns, and there wasn't the water capacity in the area. Initially, this was promoted by what was called at the time Welland and Nene Valley River Authority and the Mid-Northampton Water Board. So they were looking at where they could locate the new reservoir, and they had a kind of a criteria of things. They needed a valley with a suitable shape. The formation must be very strong to be able to withstand the dam construction. The geology must be right, so that you're not going to lose water through the base of the reservoir. One big advantage would be that you had local material to build the dam construction, that you had local rivers that had a large capacity to be able to feed into the reservoir, and that you'd got local population that needed the water without having a huge cost for transportation and pumping of the water. Out of their investigations, they came up with two locations. One was the Wash Valley upstream of Empingham, and the other was the Charter Valley to the northwest of Manton. And these were the two sites that were being looked at the time. And at the moment, there is another, it's a long way since that, but Anglian Water are now at the moment looking at their next two reservoirs, and they are just going through and getting everything ready for what's called a DCO, which is a development consent order that has to be approved by the government. So they are planning to be built in the next kind of 10 to 15 years. So they did some primary geological investigation, and it was decided in 1968 to proceed with the promotion of these two reservoirs. And initially the idea was to promote both. After a while they decided just to promote Empingham Reservoir, and they felt that they could keep Manton Reservoir option as an alternative for the future, so whether that was going to be in another 10, 20 or 30 years. But that has never materialised. The two new locations are a long way away from that location. So the journey to constructing the reservoir started, and part way through this, the Mid-Northampton Water Board was replaced by Anglian Water Authority, and in 1973, and then later on in 1983 they was renamed and it became Anglian Water. There was a lot of opposition to the project, as you can see from the list there. Rutland County Council were against it, National Farmers Union, local landowners, and the Council for Preservation of Rural England and Oakham Rural District Council. So there was a lot of objection, but there was a need, and that was what managed to progress it. And it progressed, and eventually they got parliamentary approval in May 1970. So principally the design was to flood around about 6 or 7 square kilometres of the Gwash Valley, as well as using the sides of the valley, so not just the base, quite a way up the sides. Several villages were going to have to be demolished to achieve this. There was a lot of existing water wells that also had to be plugged as part of the ground repreparation. And the other great advantage was that there was a lot of clay in the area that could be used to build the dam. The stats for the dam are there, and it was and the finished structure, you can hardly see it if you go to Empingham and look up. It just looks like a big green embankment. So, as Steve said, Empingham Reservoir later became Rutland Water, which is a reservoir in Rutland. As you can see from the plan there, you can see where Rutland is. It's just to the west of Peterborough. The reservoir is near enough in the middle of Rutland itself. And to fill this reservoir, rather than using the river gwash that comes down the valley, and as you can see from the drawing there, the plan there, oh, wrong one, that one, there, it's got two arms, and the actual dam is right at the bottom here. So the Gwash River itself doesn't supply enough water to fill the reservoir. It does add some flow to the reservoir, but it is actually maintained downstream as well. So it still is an operational river as such. So the surface area of the reservoir is the largest in England, but its actual capacity is exceeded by Kielder Water in Northumberland. The design and construction team. The design responsibilities were spread across Welland and Nene River Authority, the main consulting engineers, and Mid-Northamptonshire Water Board. And the main consulting engineers were involved in the diversion tunnels. The actual construction team were made up of, for the tunnels was Edmund Nuttall, and for the reservoir was Gleeson Civil Engineering. Something I'm not covering at all, but there was on some of the tunnel sections around the back of the reservoir, there was some tunnel relining, and there were some pipes installed. So the actual reservoir in relation to where the water is coming from. You can see the reservoir here and the dam at the bottom eastern edge. But the flows are coming from the River Welland here and the River Nene here that goes into Peterborough. So to get the flows to fill the reservoir, they needed to pump all the way up to the reservoir. So, Hull Power Moor ground investigation was undertaken, and they knew that they'd got a milestone red rock bed, which was about 22 metres below the valley floor at the dam. And that was overlaid by a upper lias clay. But as that goes west up the two arms of what is now the actual reservoir, that became thinner and thinner, and eventually at the top end of there, which is where Oakham is located, a town in Rutland, the milestone actually outcrops. But what you also got across the valley, and that section there is across the valley floor, and it's also showing the green is basically the dam when it was completed. You can see a valley bulge that's occurred between the different stratas that have come across there. It's heaved up, and that's a very interesting factor that comes into the shaft construction of shaft 6A and 6B a little bit later. Here you can see the proposal for the dam, but you can also see here two grey areas, and that's where the clay was removed to help to be able to construct the dam itself. So absolute perfect location, a very narrow area to actually fill to produce the dam, but you'd also got the clay literally at the back of the dam itself. The ground investigation did prove that there was a lot of disturbance. but it wasn't fully understood eventually until the other shafts were put down exactly where that disturbance was in relation to those shafts. What it did give was, when they were actually constructing the supply aqueduct tunnel and everything, it made it very easy because it was very disturbed and easy to excavate. So, two sections through the two tunnels. You've got two tunnels. You've got a tunnel A, which starts right down at Wansford, which is the furthest section of river from the dam itself. And then you've got section through section B. So A is on the right-hand side, and A is on the left-hand side, B is on the right-hand side. So what you've got here is you've got the River Nene just here, and you've got a pumping station. You've then got twin 1800 pipes that go up the side of the valley to start with, to what is then called shaft 1. That shaft, the water is fed into the shaft, it drops, and then it goes along the tunnel, which is a 2.54 or 100 inch, all the way to shaft 3 here. Just the other side of shaft 3 is another little section of tunnel where the ground was too deep for open excavation, and then there is another section of 1800 pipe that goes to the Tinwell pumping station, which is located right next to the River Welland. So you've got water coming from Wansford, comes up to here. At Welland, the Tinwell pumping station, there's two sets of pumps there. There's one that is extracting from the Welland, and there's another set that is pumping on the flows that come from the Wansford. What then happens is, again, it's pumped up the valley side to shaft 4, fed into shaft 4, goes along the tunnel again to Empingham pumping station, where there's a whole array of pumps in there which lift it from the bottom and then pump it into the reservoir through another set of pipes and tunnels. Same information on this, but an older version of the drawing. But you can also see here, you've got this clay, the liar's clay here, but underneath it, you've got other various layers, and then eventually you come down to the top of the milestone rock bed down here. The actual works around the reservoir, you've got your dam here, but there was also additional tunnels. They were looking at, normally you'd have a outlet tunnel coming through the middle of the dam underneath it. They decided to instead bring it out sideways and put an outlet shaft here and a feed round the side of the dam to be able to allow the flows to go back into the river if needed. This was very beneficial for the actual construction, because rather than having to put that through and delay the start of the dam construction, this could go on to one side while dam work initially started. Bit simpler version of what I've just explained. with the water being extracted here, up the 1800s to here, drops down the shaft, along, then picked up at Tinwell, so it relifts up the hillside and then on to Empingham, and then up. It doesn't actually go over the top of the dam, but it goes at that level around the side, and then up the reservoir and through some inlet jets. And you can see that described here. You were talking about 7.9 cubics being extracted from the river Nene, and from the Tinwell about 5.3 cubics. Those figures have slightly altered over the years with different extraction licenses being applied for and, you know, EA requirements, but that's principally the sort of flows that it was originally designed for. So just covering the tunnels that were constructed at the back of the reservoir. You've got an outflow structure here. You've got an outlet shaft here. You've got a 3.66 tunnel this way, and you've got a 4.42 tunnel going down this way. And these were all constructed while some initial work was going on with the reservoir dam itself. This also allowed for other things to occur because of expected settlement in the valley bottom. It was handy to have the tunnels and everything out of the way. They needed to put in a lot of deep sand drains that needed to be installed, and it kept the amount of tunnelling to a minimum by going round the side rather than down the centre of the reservoir itself. And that's a photo of the outlet shaft going down. Back in these days, most shafts were constructed with concrete segments, which were classed as what are called bolted segments, because they had pans in them and the bolts went through the webs. Today, most shafts are constructed by either what you call one-pass or smoothbore segments, but this was the way that shafts were constructed in those days. The shaft segments were a lot cheaper to make in those days this way. The outlet shaft was 10.66 metres, 35 foot. The two tunnels, as I say, were 3.6 and 4.42. They were both bolted tunnels as well, so they were segments looking exactly like the ones for the shaft there. But the upstream tunnel needed to be smooth. So in those days, you used to get a piece of concrete that was supplied by the supplier, and they used to be called buckfill because they were developed initially by a company called Buckham's that used to make the segments. And you literally put this lump of concrete into each of the pockets that you could see there with some mortar and filled it all in and then pointed it all up, and that made the tunnel smooth in the end. It looked like a normal one-pass tunnel that you see today. The downstream was not done like that. They needed to put a landing in it to be able to support one of the pipes, and so they could have another pipe underneath it and various other utilities and things they wanted there. So when they put in the landing, the shutter also did and cast an in situ lining, so they didn't actually have to fill those segments with the buck fill. Various outlets from these tunnels going into various places to feed the water if it needed to be, to bypass and to extract the overflow. The drawing of the overflow shaft and the outlet shaft there. And you can see on the right there what I was just describing about the landing being put in and that in situ lining that was done, all cast in situ. So 100-inch wedge block, it's slightly unusual. It was first painted in the 1940s. There's hundreds of kilometres of it being installed around the country. The bulk of it in London, in stiff clay and chalk. The segments form the ring with two wedge top segments. There's 9 segments plus the 2 top, and then you've got a key. You push the key in, it expands the rings apart against the surrounding clay or chalk. This works in compression. There is no bolts holding these segments together, and they are either non-reinforced or very lightly reinforced. Sometimes they've got a bit of reinforcement in for handling and transport and that side of things. So when you push in the top key or wedge, the top segments are tapered, and so is the key that's tapered. And you're trying to get it to push against the clay to a certain degree or set. So the tunnel machine is pushing that with a ram, pushing that key home, and it has a set. So, and that then gives you your required compression against the existing ground. Depending on how the machine is cutting the clay or the chalk, and if you're not quite obtaining the set that you need when you push it home, you can get, the keys can come in different sizes. So if you're struggling to push it home fully for any reason, you can go to what we used to call a -3 or a -6, so they were slightly smaller. If you weren't getting the right compression, you could, and force on the set, you could go to a +3 or a +6. So you had that facility. Literally, you had a pile of them next to you in a tunnel machine, so that as things changed, you could just change that key very slightly. So it all relies on the mobilisation of the passive earth to hold the whole of the ring together, which is why it can only be used in good, consistent, cohesive ground conditions like clay and chalk. When you do push it in, and you'll see on the next sketch, you'll see that the actual key is not the full length of the actual segments. The segments are 686, and the key is slightly smaller in length. So you had a little gap. So as the key was pushed into place, you can see here the tunnel machine is going this way, and the wedge is being pushed in this way, but that wedge is actually not the same as the width of the actual wedge block. So you had a little gap left. You can see the little gap that's there. Well, that was filled with what was called a rat bag, which was actually literally a bag, Hessian bag, sandbag, filled with cement, put up there as the wedge was pushed by the tunnel machine, and then after it was installed, it was then pointed over, and that has caused some problems in other places over the years, in that sandbag and that pointing that was covering over the sandbag and keeping it has come out. The pointing's come out. The water in the tunnel has then got hold of the sandbag, eventually eroded it away, and there has been instances in various places where what then happens is the water gets up into the ground above, erodes the material above, and eventually you lose the overburden pressure that's holding the segments in place, and unfortunately the segments then come down. And there has been a couple of instances, and I have been involved in places in London where we've actually had to go and put in a new concrete tunnel lining, in situ lining, that's a permanent lining. It's not utilising any of the existing wedge block. It's a new permanent lining. Something not applicable to Rutland, but I also worked on Lee Valley, and here we were going under various, a couple of reservoirs and also some water channels in North London. And the concern was there that at any time in the future, if somebody had to empty the reservoir, you would lose the overburden pressure, because that was designed in the calculation, the volume of water that was in those particular reservoirs. The way around this was literally, in certain sections, was to put GRP pipe in. Sometimes we put 1 or 2 in under a little short where there was a water course going across. Other times we put 10 or 20. You can see how tightly they fit on the right hand side there. We spent a lot of time designing a frame and utilising and altering a forklift to be able to drive these down the tunnel, in some cases 1.5 to 2 kilometres, to find the location they were put in. And then you'd put in 10, 20, and then you'd do a fancy taper to match it back onto the existing segments, and then you'd leave it for half a kilometre, and then you'd put a few more in. For Rutland, the segments were all made on site in a casting yard near the Welland, so that was between shafts 3 and shafts 4. As a result of that, shafts 3 and shafts 4 were used for the main tunnel drives, so that the segments didn't have to be moved very far to the area where they were needed. They were casted in nests of segments. They were stripped after 24 hours. They were kept in a shed that was made on site there, and for 2 days, 42 days before they were actually used on site, and they needed to achieve 55 Newton at 28 days. The Wansford to Tinwell, so that's Tunnel A, was 680 odd metres, and then Tinwell to Empingham was another 7,100 metres. Wedge Block was originally developed by the Metropolitan Water Board. The segments are only 140 thick, 27 inches long, and as I said before, you've got 9 ordinary, 2 tops and a key. These are some photos of the segments being made. This is in the 1980s. This was in what used to be called Charcon, who used to make segments. In those days there were 2 big companies, there was Buckham's and Charcons. This was at Mansfield. I went up there for something to do with Lee Valley. So this is very similar. You can see the batch of segments being cast. So exactly the same scenario as it would have been at Rutland. And you can see them all stacked up here. This is a permanent setup. You can see a configurated wedge block ring there. This was some tests that were going on. We were testing the forces required to put it in with the different sizes. So, you know, between +6 to -6, we were looking at how that worked. We were doing some tolerances when they were built together, and we were doing some tolerances on the angles on the faces by a rig that was set up then. And remember, this is the back end of the 80s, probably all digitally done these days. So onto the TBM that was used at Rutland. It was 3 meters long, it had a rotating cutter. It was equipped with erecting equipment to lift and install the lining, although some of the segments did still have to be lifted and pushed in place by the workforce. Not as complicated as the machines you see at HS2 and Crossrail and what have you. The machine cuts, and it's got a bead. You can adjust the bead because you don't want too much overcut, because you're trying to push your segments back out against the clay to get the overburden to start working on the segments. The wedge or key is driven at the top by a ram off the top of the TBM, and then you've got behind that, you've got various sledges with conveyors, winches, generators and other item. The whole TBM itself was about 44 meters long, and it had a gang of 5 operating it. Some bits of work were done well in advance of the tunnel being started. At shaft 6A and 6B, which is up at Empingham right by the reservoir, they were constructed. They were, and between them was then done a cross passage of 15 foot between the 2 of them. And then off that cross passage was the leg of a T put in, and that went about 200 meters to receive the TBM. On Tunnel A, there was all supposed to be a tunnel at shaft 2, and that was the idea of that was to prove the ground and also to be able to use for muck away. And because of the location and the ground that was there, the idea was that you would possibly have to build some segments there and allow the TBM to come into it. So it was a way of reducing the risk by being able to have the machine come straight in and through a section of faulted ground. The whole of the tunnel was driven in upper Liar's Clave, and that was mainly dictated by the hydraulic gradients that were needed. top of the clay was chosen because it was far enough away from the milestone rock, because that was under pressure, water pressure. And the idea was to try and be below some various markers that were seen in the various GI that was done. At shaft 3 there were 4 well points put in, because at that point they were expecting the water table to be at the axis of the tunnel. In the contract there was allowance to be able to dewater the whole length of the tunnel, but there was quite a few areas where this would have been absolutely nearly impossible with the roads and the depths that you were talking about. There were piezometers put in, and at shaft 3 they did lower the water when they put, for those well points that were put in. That pulled it down by 14.5 metres, and that caused a cone depression of over 3 kilometres in the area. When they did actually construct shaft 3 in November 72, it took 8 weeks to put the shaft down and put the tunnel eyes in. That's the TBM actually arriving at that's shaft B. That's at the, coming into Empingham. So this is where they built a stub tunnel to receive the machine into. Just put that back in to refresh you of where all the various layers are and how the tunnel is shown to go through various areas here and here, because that's very relevant in a few minutes to do with how the tunnel progressed when it started to be constructed. The shafts were deep. You can see shaft 1 was 20 metres, shaft 3 19, shaft 4 was 31 metres. They were all 10.66 metres in diameter. They were so big, it was all to do with the oscillation surge if and when the pumps had to shut down. So there's no actual pumping here. You extract at each location, and that allows the water to flow through the tunnel. So you extract at the upstream end of each of the tunnels. The shafts then had landings and things installed. The contractor, Nuttall's, decided that they didn't need shaft 2 and shaft 5. Big cost saving. But they did put 400mm boreholes down, and these are permanent air venting points on the tunnel even today, because they were positioned at the high point of the tunnel. And also, they also gave some more information with regard ground conditions, and it allowed, in some places, the tunnel to be regraded to have a 6-metre cover to the milestone. So 6A and 6B started very early. The idea being that they needed to be able to start on the pumping station, and these were sunk near enough simultaneously. One was a couple of metres ahead of the other. The first one progressed to about 20 foot from its formation excavation level, and the base blew. The shaft flooded and it was overflowing the top. The second one was flooded on purpose as a safeguard, and the water was coming from the milestone rock bed. which was, in theory, 15 metres below the formation of the shaft. To be able to progress the shafts, they put in 18 dewatering wells down to about 40 metres. This lowered the water table by 36 metres. At one point they were pumping 2.22 cubic metres, which did ease off. With this dewatering installed, they also took advantage and put in the cross-connection tunnel between the two shafts, and also the stub tunnel that was required. That also, with all that excavation, proved that what they'd actually put the shafts down through was the valley bottom and the valley bulging. They put it right in the valley bottom, and you've got the valley bulging occurring. So you've got the stratas coming near enough vertical. And unfortunately, what that meant is that the water from below had an easy pass to come straight up and into the bottom of the shaft. So from this, they learnt a lot about what they would needed to be done, which is why the stub tunnel was done. So it was done so that they drove that with the dewatering in place, so that when the TBM came, because it's a machine that had to be in relatively dry conditions, it's not a full-face tunnel machine like you can see today that can go through high water table conditions. So this was a way of working and getting the receiving point outside of this the bulge that was occurring. Shaft B, as I say, shaft 5 was removed and was just, again, another borehole was put in place. And again, from information they got from putting that borehole for ventilation and for survey alignment, they again played with slightly with the gradient of the tunnel. I mentioned that we did an inspection back in 2018, I think it was. That's one of the, I can't remember whether that's shaft 2 or shaft 5, but that's the shaft that was then replaced by a borehole and has permanent ventilation. This is inside one of the shafts. This is shaft 1, and these are where the two 1800s come in at a high level, and the flow goes into the shaft. It doesn't drop in because the water level, as you can see, is kept right up to the top level there. The TBM was put down in January '73, and initially it was doing 37 rings in a 10-hour for the first couple of weeks. They then started coming across some marker beds, and they then found that these were actually higher than expected, and the cutters were only scratching and causing lots of dust. They were down to about 1 ring a shift. In mid-June, the band faulted out, and they were back up to around about 30 rings in a shift. They then started having problems in the top section. They were getting a lot of overbreak and blocks of clay coming out, and this was causing problems at the back. They were having problems trying to push the rings and get the right sets on the ring. They were unable to fill the voids. They did try extending what's called the tail skin on the back of the TBM to be able to build the ring, but then they were finding that they weren't be able to get the right set still. There was a lot of hand trimming going on, and a lot of grouting, because what they also did, they went to bolted segments. You can get a version of Wedge Block that you can actually bolt, which you're using if the TBM goes into bad ground, and it, like here, when you've got blocks and things, you can actually use a bolted segment. It's a lot slower, and you've got to grout it. It doesn't work on the overburden pressure. So normally it's only used when you're breaking out of a shaft or the TBM's coming into a shaft. They did a full-scale trial on it, playing with various ways of doing it. And the outcome was that they would use puddle clay and what they classed in those days as pickled timber to fill the voids, and then they would build the segment and force it into place. They had put on rock discs, and because before they'd got clay picks on, this increased the production back to 35 to 40, and they had a maximum of 51. I think at Lee Valley we ended up getting 65 at one point. The cemented clay bands, some of it was tested here at Newcastle, and that was coming in at 84.5 Newton. They then started having a problem with the moisture content in the face, and it was causing the clay to come onto the head and onto the shield, and that slowed production. So the rock discs were removed after 2 kilometres, and the clay picks were put back on, and production went back up. The initial plan was to finish by September 73. But with all these delays, the idea was that that first one would be finished, you'd turn around and you'd do the second one and get that finished by July 73, which wasn't going to be achieved because the whole program had been worked on one machine and 24 months. So the contractor obtained a second machine, and they started shaft B early enough to be able to still achieve the production. Now you've got 2 machines running, and because of all the delays, luckily, the production plant was still producing 60 rings a day, 300 a week. So they'd got a huge capacity. So having 2 machines in the ground wasn't going to be a problem. A couple of photos from Lee Valley. So again, not Rutland, but it just gives you an idea of the sort of backup equipment that's on the machines. Tunnel B, again, has similar problems after about 2.5 kilometres, but they put the discs on straight away, and they managed to keep going at 20 to 25 per shift. Still getting overbreak, but by this time they knew how to cope with it, and the miners became very proficient with it. When they got to the end of Tunnel B, Tunnel A was going from 3 to 1, and then it was taken out at 1. Because you'd got the cross connection at between 6A and 6B, it was going to be very hard to take the machine out there. So what they actually did, and so it didn't affect the construction of the pumping station on top of those 2 shafts, it was dismantled and removed back from shaft 4. The 2 tunnels were fairly consistent in the end, 54 weeks and 53 weeks each. Slightly different number of rings. So just over 2,000 rings installed on the project. But the client had a few concerns about all the ground that was lost and whether all the right procedures had been put in to ensure that you still had the right overburden pressure and everything onto the rings. So they did some grouting tests. Basically, they couldn't get any grout in behind the rings, so they went at various places along the tunnel with the client, installing grouting and see if they could inject any. They also then did a full hydraulic test, and they filled the shafts up to the top of them, emptied them, and then inspected. They got all the water from the wells that they had at Shaft 3 at Tinwell, sorry. It all passed okay, and it was finished at the end of March 1973, and the first pumping apparently started in May 73. Again, just a couple of photos of the TBM at Lee Valley. Slightly different because this is a back actor, but it gives you an idea of the size and the complexity in the front of a TBM. There we were lucky, we put in a back shunt to give us more space when the locos came out with all the material on. You could get more locos. So you could put them into the back shunt and then steadily remove them. But it just gives you an idea of the work involved in driving a tunnel. A couple of other slightly more interesting things about Rutland. Probably seen it was on the TV and various other places. They found the Rutland Sea Dragon in 2022. They'd got the reservoir down quite a bit. They were doing a lot of revetment work around the edge, and somebody happened to spot this. And as you can see, it was excavated, and I don't know where it's actually located now, but it was quite a find in there. So that's what Rutland looks like today. Nice big reservoir. That's the dam there. The outfall shaft here. Pipes coming up what you call the north and the south arm. I know it very well. I go canoeing there once or twice a month as well. So I've got a lot of connections with it. And then from here, that's Empingham here. So they can't really see the dam. It is just a big grassed area. And then from here, the tunnel goes off in this direction. So you've got water coming in through here, through the River Gwash, but it's so little, it would never have filled the reservoir up. So, any questions?
For anyone who has questions, could you please quote your name and where you're from, please?
Could you wait for the microphone as well, so it's on the recording?
My name is John McFoy from Gateshead Council. Thanks, Rod, for that. In total, do you know how much the project cost in terms of from start to finish, from the 60s and 70s?
No idea.
No idea. Thank you.
Were you considering building one?
It would be interesting to know. I must admit, in all the reports, you can see some of them listed there. You know, there's proceedings at the ICE. There's a couple of articles in Tunnels and Tunnelling, but in all those articles, there's no mention of anything about the actual costs. And they go into a lot of detail, those different presentations do, but nowhere on anything to do with his any cost.
Anyone else? Yes.
Simon Harris, a retired ICE. I presume this is a happy ever after story, that many years later the shafts are still intact.
Well, I say We inspected them in, I think it was 2018. Apart from a little section at Stamford at Tinwell, they hadn't been looked at in all that time. We went the whole length. We had some quite interesting boggies that had been actually developed by Northwest, well, UU, and we went through the whole thing. We had bags of repair mortar sat, and if we went through 2 bags in the whole length, it's in immaculate condition. The tunnel is absolutely. They don't have the problems that unfortunately occurs in London, because you get mussels in London, in the tunnels there, in the raw water tunnels. And we've spent a lot of time going in and cleaning these mussels out. And a 100-inch tunnel, and you can be that thick in mussels. You know, you can be 5 foot thick for, you know, the whole length of the tunnel. And the problem, of course, is that as soon as you drain the water out of them, they all die. So then you've got the issues of doing this with, you know, thousands and thousands of dead mussels in there, and then disposing of it. So, you know, that does unfortunately affect other tunnels where you've got, called the zebra mussel, aren't they, I think. But this one is absolutely immaculate. When we did the inspection, we had to make sure, you know, we had dip buckets for our boots, all new kit and everything, to make sure that, you know, we didn't take anything in there. And it wasn't, this is only raw water, so it's not, it doesn't come under the potable water, fully under the potable water requirements, but just to make sure that we didn't, there was no chance of ever taking any mussels in there from anywhere. So yeah, it's in a lovely condition.
Thanks. Can I ask you another question? So if I heard this right, the shafts flooded and you had to pump them out. Is that right? Yeah.
The shaft 6A and 6B flooded, yes.
Did they change the design of them at all to take account of those different water pressures? Do you know?
No. Well, they looked at the different bases, yes. You can see on some of the original drawings and the later drawings. But no, it was just a question of being able to draw the water down and then being able to, you know, install the structural base.
So it's more a construction issue than anything else.
Yeah.
Okay, thank you very much.
Thanks, Rod, can you hear me?
Yep.
Oh, that's okay, right. Just a couple of questions on the wedge blocks. I know that you said they were designed in 1940.
Yes.
Produced 1940. And you mentioned that they were 100 inches, but they were wide, but they were, the diameter was 1800 millimetre. Why do we have imperial and metric together? Just as a matter of interest. Because if you remember, in 1940 we were all imperial, but in 1971 we had SI units reduced.
They were designed as 100-inch, but nowadays everybody calls them 2.54. I know you go through these different, you know, the various reports, and I'm as bad. I'm in that era where I started off in feet and inches and then went into metres, and, you know, 1 minute I'm talking of inches and next minute I'm talking in metres, and I've done the same here. I've put metres most places, but I've put the odd feet next to them because, you know, all shafts were originally, you know, 12 foot, and then they became 3.66. So,
well, it's actually 1973. I just finished college just before that, and I had to spend an extra year going from imperial to metric. It was a right pain in the butts. The other question was the TBMs. How did they disperse of the material that they mined?
It came out the back on a conveyor. It then went into skips. So they had a long conveyor on the back. It went into skips and it came back out in a row of skips to the pit bottom and then lifted. You know, these were the days when the TBMs were only good for good ground conditions. You know, later on you started having what they call the Lovets and the Isekis, which were for bad ground with a water table. And then from there you've gone on to the likes of, you know, the big companies like Connect in Germany, who produce a lot of, you know, probably well over half the world's TBMs. So yeah, that's how it was. Whereas now you can, in bad ground, you can pump the material out the face is sealed, you can have a water table above you, and you can pump all the material all the way to surface and then put it through a process plant. And then reuse the slurry material to put back down and pick up the next bit of material. And you have an endless loop, which is very environmentally friendly. Here it's electric locos, up and down on rails, very slow. But you used to have California switches where you could pass locos in the tunnel. At this sort of size you can do it. Smaller sizes you can't, but you could do that there.
Any other questions from the floor? Ah, here we are.
Hello, thank you very much. My name is Bob Dowdell. I'd be interested to know if there's any instrumentation in the dam, the embankment dam. Is it stable?
I can't actually, I assume there is. I've not investigated or looked at anything like that. You know, I'm a tunneler, you know, I'm really interested in all the tunnel bits of it. You know, I gave you a bit of an outline of the kind of other bits of the project, but I'm sure there is. You know, all dams these days are monitored, and especially, you know, after the near issues up at. Yes, yeah. I regularly drive past it. I come from just over the other side into Cheshire, so I know the place very well. So yes, yeah.
Right, any more questions from the floor?
Oh, another one.
Right, I wonder. Thank you.
Hi, Russ Charnock, I'm IT as well. Digging the shafts, how did they, you said they blew the base, or the base blew. Obviously, you were digging down through groundwater. How did you stop groundwater during construction? Do you think that was compressed air, or? No,
there was no groundwater during construction until the base blew. So yeah, that was the problem. They weren't expecting it. They didn't realise they were right on the bulge, and the problem was that bulge had allowed the strata with the water in it to be able to come up underneath the base. If it had been nice and flat there, they would have probably gone down, excavated, finished without a problem. But it was that bulge that they thought was slightly elsewhere, and unfortunately was right where they put the two shafts.
Right, thank you.
I have a contribution from Alistair Lanes. Thank you for a fascinating presentation.
Thank you.
Excellent. Well, I know Rod actually isn't going to be staying any longer, so if you can think of any questions now, please think of them, because he's got quite a bit of travelling to do, I believe.
Well, I'm 9:15. I've got 2 hours, so, you know, 2 hours in the bar.
Well, we are going into the bar. Right, thank you very much indeed, Rod. I'm from an electrical background, power station, substation building and what have you. But I can't cease to be amazed at the complexity of what you guys have to do here and the problems you meet while you're doing it.
Yeah.
Nothing but admiration for you.
Thank you. Yeah. What really amazed me was the fact that, you know, I always assumed, having lived in the area for quite a while, that the whole reservoir was fed by rivers.
Yes.
You don't realise suddenly that it's fed from downstream by two of the main rivers that go through the area.
That is, it's truly incredible to do that and to think of actually doing it.
Yes.
I'm amazed actually at the planning. But anyway, I have a situation now where we've got to thank you very, very much for what you've given us this evening. And can I call upon Stuart Porthouse to give a vote of thanks?
Thanks, Rod, for coming along this evening and giving us a fantastic paper. We thoroughly enjoyed it. The one thing that you pointed out is that when anybody that comes to the Institute and talks about dropping shafts or driving tunnels is always welcome to come here. Because we've been a mining institute since 1852. What I quite liked about the talk in particular was that this was completed in 1973. And when you think about it, in 1970, getting planning permission was just as difficult then it is to get planning permission now. And that was the time when Edward Heath was the Prime Minister. So it just goes to show there's things that need to change to improve. Let's hope that goes ahead. Because there's so many things, major infrastructures that we need to be getting on with that just seems to take forever and ever. And whichever you do, people will complain about it and object to it. Doesn't matter, whatever you want to do in the country. I think we've thoroughly enjoyed the talk. It's good to see that it's still there. It's feeding all the people that live around the area, and but it's also good to see that we have a reservoir in the northeast that's much bigger.
In capacity, not in surface area.
Capacity, yes. Okay. So on behalf of everyone here, ladies and gentlemen, can you join with me in thanking Rod for coming up and giving the talk tonight? Thank you.
All right. Well, that was absolutely wonderful, and thank you from myself. Right. Well, here we are. I believe the bar is going to be open. Can you please be certain that you do sign the books and the registers before you leave? It's very important to us to have all your names there available. So if you can take care and turn up for the next lecture. I haven't actually got a list of what is coming up next in March, but you've seen what happens here tonight. It'll be absolutely splendid, so make sure you turn up in March. And keep your eye on the website, the Nene website, and you'll find out exactly what it's all about. But it'll be interesting, you can be sure. So thank you very much, everyone, for coming along this evening, and have a safe journey home, or have a safe journey to the bar. Thank you very much, everyone.